All right, great. So yeah, thanks again for asking me along to the meeting. It's great to be here. I'm going to be talking today about testing tensions with the matter radiation equality scale, as well as with new measurements of CMB lensing. And so this talk will, broadly speaking, divide in two parts. The second part will focus sort of more on my home turf, CMB lensing measurements, and what they can tell us about S8 and neutrino mass. In the first part, I'll be talking about large-scale structure and how we can measure H0 without the sound horizon. And I'm hoping, given there are all these large-scale structure experts on the call, that you can give me a hard time and yell at me and tell me what we're doing wrong. So that's sort of my hope. So feel free to interrupt and ask questions, etc. All right, good. So let me start off by discussing the sort of H0 without the sound horizon project, which was with, in particular, my PhD student Garrett Farron and my former master's student Oliver Philcox. So I'm sure you all know the background here, but I know there's some students on the call, so I'll just very quickly go through the background. As you all know, they're the sort of two most powerful ways in terms of statistical error of measuring the Hubble constant are using the CMB power spectrum, which is an early time indirect probe. In other words, it makes use of assumptions about the sort of cosmological model and extrapolates to low redshift. And the other very powerful probe in terms of statistical error is the cosmic distance ladder, which is a more direct late time measurement. A big current puzzle in cosmology is that these two measurements from the Planck CMB power spectrum and the cosmic distance ladder with Shoes are currently in tension. The CMB power spectrum measurement with Planck giving you around 67 kilometers a second per megaparsec, whereas Shoes gives you something like 74 kilometers a second per megaparsec. And in the past, for a long time, I was a bit of a skeptic. I thought this was a fluctuation, but the significance just kept growing, and now it's reached 5 sigma. So clearly there's something wrong. And this is a slide I stole from Andrea with permission. What is the resolution for this tension? My personal viewpoint is still that it's most likely it's a systematic, but it is a little bit hard to pin this down to a problem with just one probe. That's certainly true on the CMB side, because a low H0 value is preferred not just by Planck CMB, right? But as I'm sure you all know, a similar low H0 value is obtained from the recent ACT and SBT CMB power spectra, as well as from large-scale structure from BOSS when it's combined with a BBN prior. So that doesn't even rely on the CMB at all, and yet you still get a low value of H0. Of course, the strong lensing picture has gotten a little bit more complicated with recent analyses, but in any case, it's a little bit hard to say. It's not 100% clear to say there's just a problem with one survey. At least that's very clear on the CMB side, I think. But it was pointed out some time ago that all the experiments or all the measurements, more or less, that give you low H0 have one key thing in common. Namely, they all assume that we understand the early universe physics, and in particular that we understand early universe physics to compute the sound horizon scale, right? And so just for the students in the room, just to remind you the sound horizon scale and its importance in determining H0 from the CMB, the sound horizon, of course, is the distance a sound wave travels from the early universe to when the CMB photons are released. It's given just by an integral over the speed of sound and the expansion rate. And this sound horizon is so crucial because it imprints a characteristic scale in the CMB power spectrum. Namely, it determines the spacing of the CMB acoustic oscillation peaks. It's also present, of course, in large-scale structure or something very closely related, which I'm not going to distinguish between the two as the BAO feature. Now, how can we use the sound horizon using the CMB to get Hubble? Just to remind you, there's sort of a few steps. First of all, we use our knowledge of the early universe physics to infer CS and H of Z from the densities of matter and baryons, for example, and then we can compute the sound horizon RS. Okay, so then we have this known physical scale in the CMB. We can go out and measure what angle it subtends by looking at the spacing of the CMB power spectrum peaks. So if we know RS and we know the angle, we can then infer the distance to the CMB last scattering surface. And if we figured out this distance chi, the final step is that that distance depends on h naught, and so we can solve for h naught. So those are the steps. Compute the sound horizon, measure the angle it subtends, and figure out the distance, and then finally solve for h naught. In large-scale structure, the analysis, as I'm sure you all know, is at least morally quite similar. In large-scale structure, in the analysis of large-scale structure, we mainly, at least until very recently, got h naught from the BAO scale, which is the imprint of the sound horizon, or RD technically, on the large-scale structure. So again, there's sort of these wiggles in the matter power spectrum P of K, and their spacing is determined basically by the sound horizon. Now, if all of these probes rely on the sound horizon scale and give you low h naught, an idea that I think has attracted a lot of attention for resolving the Hubble constant tension is to propose that, what if new physics is changing the sound horizon, right? So we've computed it wrong, assuming just standard lambda CDM, and that's why we're getting this tension. And if we compute the sound horizon correctly, we would resolve the tension. And in particular, perhaps the most promising explanation, it has been argued, for how you would do this is that you could maybe resolve the tension by changing the sound horizon via a change in the early time expansion rate, right? So if you look at RS, if I just increase the Hubble rate, then I can shrink the sound horizon scale, and that brings measurements of the CMB and distance ladder measurements into better agreement. But notably, I can't do this. I can't change the expansion rate at any redshift. So if I look at what redshifts contribute to the sound horizon scale, so if I look at d log RS by d log H, you'll see that I can't really change things very effectively at high redshifts. Where I need to change the expansion rate to really make a difference for the sound horizon scale is pretty much just before recombination. So it's redshifts of just a few thousand where I need to make these changes. Right, and so I think there are several examples. One example is that you have a phase of early dark energy that for example, a scalar field that behaves like early dark energy at early times and then just rapidly decays away, becomes unimportant at late times. And so again, what you see if you look at the fraction of energy density in this early dark energy component, it's not the case that it contributes a lot at very high redshifts, right? What happens is that you're really affecting the dynamics of the universe only at redshifts of a few, mainly at redshifts of a few thousand, because that's where you need to change physics to have an impact on the sound horizon. There's redshifts of a couple thousand. Now the problem is that there's at this point an enormous number of models, right, that do this kind of stuff. Right, so there's early dark energy, but then there are papers back and forth whether they're ruled out, and then there's there's a new tweaked model, and so it's just a huge list of models. And obviously, what you can do, and in some cases, the most powerful thing to do is to just go in and try to test each of these models individually. But also, given the fact that my personal opinion, none of these models is way more theoretically better motivated than the other ones. I do think it's nice to try to come up with some kind of generic tests for physics that could be changing the sound horizon scale, right? I mean, can you come up with some kind of generic test for this kind of explanation? And so this is something that we started thinking about a little bit. And one way that maybe you could make some progress in coming up with such a test for new physics that changes the sound horizon scale is that you can note that in large scale structure, in the matter power spectrum, there's not just the sound horizon scale, right, which determines the BAO wiggles, but there's also another scale that's, of course, really important for determining the shape of the matter power spectrum, which is the matter radiation equality scale, K equality. Right, so this is set by the horizon size at matter radiation equality, and it's imprinted in the shape of the matter power spectrum because modes that enter during radiation domination have their growth is suppressed. And so the the equality scale is imprinted as sort of a peak in the matter power spectrum. But notably, we don't actually have to measure the peak to determine this. There's also a sort of logarithmic dependence that means that it also impacts the higher k, and indeed there's a whole sort of shape of this peak. That means you don't need to go to k of 0.001 to see this. Okay, so if we're trying to come up with a test for new physics that changes the sound horizon scale at early times, we thought, well, maybe we could measure h0 not from the sound horizon scale, but try to come up with an independent measurement that doesn't involve the sound horizon physics at all by using instead this other scale in the large scale structure, the matter radiation equality scale. And the basic idea is very simple. You could say, well, the BAO is my usual standard ruler for measuring h0, and now I'm going to just use a new standard ruler, which is the equality scale, to determine the Hubble constant. Okay, so the details here are that K equality depends on the physical matter density omega matter h0 squared. And what I actually measure is Kx over h0, because I'm measuring angles and redshifts. And so what I measure, it depends on omega matter h0. Okay, now if I additionally have a probe of omega matter that is independent of the sound horizon scale, I can combine those two things and I can solve for h0. Okay, so again, I measure this K equality from the peak and from the sort of logarithmic suppression of the matter power spectrum. That tells me omega matter h0, and if I have an additional probe of omega matter, I can solve for an h0 value that does not depend on the sound horizon scale. So that's sort of the motivation. We want to, but at the very least, it's a nice consistency test, right? We want to establish another scale from which you can measure h0, check that we get the same result or not, and I think the motivation here for us is whether we can test new physics changes RS, but it's also just generally a nice test. And of course, I should mention that a lot of this idea is not totally new in the shape parameter. This was in the sort of language of the shape parameter. Some of the earliest large-scale structure constraints actually use this. This is really easy, right? I just have a measurement of the matter power spectrum and get K equality, and I add a probe of omega matter that doesn't depend on the sound horizon, and I can solve for h0. Now, there are a few options for omega matter, so we looked at a few of them. The first one is supernovae without the distance ladder, where I just have sort of the shape of the luminosity distance relation. And that gives you omega matter without the sound horizon. You can also use uncalibrated BAO, or you could use lensing at different redshifts. And those are all ways of getting omega matter without the sound horizon. Okay, but the thing that's we spent a lot of time on is to just make sure that this is actually working the way we expect. Because how can we be sure? We're analyzing, say, the galaxy power spectrum or some projection of it. How can I be sure that I only get information from K equality and not from the sound horizon, even though this BAO sound horizon information is really powerful? So there are kind of three methods that we explored or have started to explore for getting rid of the sound horizon information, right? The first method is projection. The second method is using weak priors on the baryon density, so just don't use BBN information. And the third one is trying to implement some marginalization scheme. All right, so let me just walk you through those quickly. The first method is probably the simplest one. Basically, if you're worried about the sound horizon features, in other words, mainly the BAO features, those get washed out by projection, right? So if I take a projected tracer, for example, the Semilensing power spectrum, that has no BAO oscillations, and it also, you don't have to worry about biasing, so it's quite simple. But of course, the shape of the Semilensing power spectrum, I'll come back to that again later, depends on sort of L equality, which is omega matter to some power times h0, right? So the same argument works. I can measure L equality from the Semilensing power combined with omega matter from Pantheon supernovae and solve for H naught. And this is what we got. So again, this seems like quite a weak constraint, but it is a physically, I think, very different one, I would argue, from the other ones that have been derived from large scale structure, at least to my knowledge, right? Because it is a constraint that doesn't come from the sound horizon scale, and it comes from the other physical scale in large scale structure. Of course, the problem with this measurement, you might say, oh, it's high, that's interesting, but that's not the correct interpretation because the error bars are just too big, right? So we need to shrink those error bars for this to be competitive and interesting. And that's sort of what we've been thinking about recently. And so one way of doing this is, the advantage of projection is that it gets rid of sound horizon, but the disadvantage is that you just have fewer modes in a 2D observable. And so it would be nice if we could go back to a 3D measurement of, say, galaxy clustering. And so one way to get information without the sound horizon scale, although it's not as simple as it seems, from galaxy clustering and from galaxy surveys is to just avoid calibrating, try really, really, really hard to avoid calibrating the BAO scale. Right, and so normally, when you analyze sort of Boss galaxy power spectra, you combine with CMB, or at least you use a BBN prior so that the sound horizon is calibrated and you can use BAO. But we use sort of basically no constraint on the baryon density and just sort of hope and choose other priors a little bit more carefully with the hope that the sound horizon is uncalibrated. And so in practice, so this is why we brought Oliver on board, we're using the Ivanov et al. EFT full shape analysis of Boss DR12 galaxy power spectra. And we're also combining that again with omega matter from Pantheon supernovae. But as I said, an important point is that there's no BBN in what we're doing. Of course, you might still worry that that's not good enough. Like, is it good enough to just not add BBN priors on the baryon density? Because as was pointed out, there are other baryonic features in the matter power spectrum. For example, there's a broadband suppression, and you might worry there's a self-calibration that the shape determines the baryon density, and that calibrates the BAO, and you are in fact getting information from the sound horizon. So we spend a lot of time showing that indeed the constraints on Hubble we get don't come from the sound horizon. And so what we did there is we did several things to show that the constraints we get on Hubble from this analysis without BBN don't depend on the sound horizon. So the first one is we did the same analysis in MOCs that have no wiggles and in MOCs that have no baryons. And the constraints we got with our analysis methods and choices were basically unchanged by getting rid of the wiggles and the baryons. And so I think that's pretty convincing. Another piece of evidence is that if you look at the constraints with Kmax of 0.25 in blue, and you lower your Kmax with this sort of analysis to 0.1 in red, the constraints don't change all that much. And that's, that would not be the case if you had a BAO analysis, I believe. We also did several other tests, which I won't go through. But so here are our results then of basically Boss full shape with Pantheon supernovae. This is what we get for H naught. But you can see the sort of contours here. Here are the relevant H naught results. And so this is the result from just Boss and Pantheon supernovae. 65 plus 3 minus 5.4. So I should emphasize, though, that this is sort of still consistent at around 2 sigma due to a bit of a tail with 74 kilometers per second. So I think it's an interesting proof of concept, but it's still not at the point where we can say anything, rule out things or make any very strong statements. So to summarize the sort of 2 new results that I mentioned, here are some of the measurements from, this is not comprehensive, and I apologize for that. This is a plot from Oliver. These are some of the measurements of H naught from a CMB and large scale structure. And here are the sort of two ones we added. And of course, from the error bar perspective, they don't look all that compelling, but I would argue that their physical origin is very different, right? They are coming from a very different physical scale. They don't depend on the sound horizon scale at all. Now, to make this more interesting, though, for the original problem, and to make this a more interesting consistency test, we really want to shrink these error bars and make this kind of measurement competitive with the standard BAO or sound horizon scale derived measurement. So, how can we improve this, right, and get the error bars on H0 to be competitive? Well, okay, so one thing you can do is just use the same method. Don't use BBN information and just add better data. So for Euclid, then you get 1.6 kilometers a second, which is pretty interesting, but still not as good as BAO. And we should look into that. What we've been thinking about, though, in terms of improvements is you would want to use all the data that we can get, including, say, a BBN prior, et cetera. And we would like to intuitively marginalize over the sound horizon. Now, this idea can never be exact, because the sound horizon is not really a fundamental quantity that goes into the Boltzmann equations, right? It's really an emergent quantity. But you can come up with some approximate procedure and then test it on a full analysis. So this is what we're kind of thinking about now. Basically, our hope is that what we can do is just modify the covariance matrix of a normal sort of P of K analysis in such a way that it basically projects out the wiggles. So this relies on the fact there's this nice result that I only recently became aware of. I'm sure a lot of you are familiar with it. Sort of, if you marginalize over a parameter in your model, so if you have data minus model, and let's just say you have a parameter alpha that rescales the sound horizon in a model. And then I have a sort of standard likelihood with a chi-squared. If you have a fairly small alpha, so alpha can't be changed by order 1, marginalizing over alpha, you can sort of Taylor expand and show that that is equivalent to an analysis with a covariance matrix that's modified in this way, right? The covariance matrix is modified by this derivative of your model, in other words, your power spectrum, with respect to alpha, the rescaling of the sound horizon. Well, basically what I want to do, this sort of basic idea that we're thinking about now, and I'm still not sure this is going to work, is that I want to marginalize over RS. So I want to do a full analysis, and then I want to get rid of the sound horizon information. Okay, so I want to have a likelihood with some alpha rescaling of the sound horizon, and I want to marginalize over that alpha. So I want to get rid of that information. And there's a mathematical result that marginalizing over that information is equivalent to doing an analysis with your standard covariance matrix with an additional term. So basically, you can absorb that marginalization into just changing the covariance matrix under some approximations. Yeah, the question, I guess, is how much are you really getting rid of the BAO information? Are you really getting rid of all the sound horizon information? So we have some constraints from doing this, and it looks like we get really, really good results, but I'm still not convinced we're not, there's no BAO leaking in. So this is in progress. I mean, you can see that basically for Euclid, from K equality, if you do this marginalization, you get this dotted green contour compared to, the sort of more conservative analysis where you don't try to do it and just don't include any BBN information. So if we can get this to work, potentially from K equality, there's actually a lot of information if this holds up. It looks like you could get below 1 kilometer a second in terms of H0 errors, sort of close to what you get from BAO. But I'm still not 100% sure that this is going to hold up and really work. But that's what we're thinking about now. Like, can we actually come up with some way of really getting rid of, sort of doing the opposite of a BAO analysis, right? Like, get rid of the sound horizon derived information. Let me just quickly come back to the original motivation, which is something else we're working on, is just checking whether this actually, indeed is sensitive to new physics. So, I gave a kind of hand-wavy argument, but we're looking in a little more detail about whether this actually holds up. So is this actually a useful consistency test? So for example, if I look at lambda CDM, I would expect to get the same result from K equality in red and from BAO in green. Now I should note that this is not with this is the old-fashioned way of getting K equality, so that errors are still pretty big. Okay, so hopefully we can improve that. But what's nice is that if you run this on EDE, you do, even though this is fit to the CMB, so it can't have a large difference, if you look at the best fit EDE model, you do see some differences, right? So there is at least, it does seem to confirm that there is some difference in the in how new physics affects these two scales. It seems to affect them differently, and you seem to get a different value of H0. I mean, this is also super preliminary, but if we can shrink these, so the hope is that we can, shrink these error bars further, and then we get a really powerful consistency test, and you go out, and if you see a discrepancy that tells you, yes, there's indeed new physics, and what the sign is and the magnitude will tell you what redshift it takes. So it would be really cool if we could get this to be a very powerful diagnostic for what's going on. But I think we're still a ways away from that. So now let me totally switch gears and talk about some semilensing measurements with advanced AT and what they can tell us about S8 and neutrino mass. As you know, there's a huge amount of information in the distribution of mass and dark matter. And the best way of getting that information out is directly, at least, without worrying about biasing, is using gravitational lensing. The CMB is kind of a unique source for studying gravitational lensing. It has some advantages compared to weak lensing. But the nice thing about the CMB, from my perspective, is as a source, we really, really understand its properties, right? We know exactly what redshift it's at. We know exactly what its statistical properties are before lensing, right? And we really, we understand the fluctuations really well. And so it's just very well behaved. And in addition, there's another nice property of the CMB as a source. It's the most distant thing that we can see. It lies behind all the dark matter and all the mass. And so it probes, as the CMB photons pass through the universe, they're deflected not just by the low redshift stuff, by the entire distribution of mass and dark matter. You can describe the effect of CMB lensing, using a remapping with an observable D, the lensing deflection field. Okay, so this lensing deflection field points from where the CMB photon is emitted to where it's the direction in which it's ultimately received. So the lensing deflection field is the observable, and lensing causes the CMB to be deflected by this amount. But how can we measure this observable? If I call this deflection field the lensing observable, how can we actually measure it? Well, let me start by giving you the mathematics of what we do. What we do is we make use of the fact that this lensing breaks translation invariance, right? It changes the statistics of the CMB. So before lensing, the CMB is sort of translation invariant. But now if I have a fixed lens, that breaks translation invariance. Some directions are magnified and sheared and some aren't. And so that changes the statistics. And mathematically, that corresponds to the fact that without lensing, translation invariance means that two different modes are uncorrelated. But lensing breaks that and introduces new correlations between two different modes. And so therefore, we can measure lensing by looking for these new correlations between two different modes of the CMB temperature field. Okay, and this is the so-called quadratic estimator written in a schematic way for this lensing deflection field. What's the intuition behind this kind of translation invariance breaking? Well, I mean, one way to think about it is that in some regions of the sky, what lensing does is it magnifies the CMB. And that means that the local CMB power spectrum is shifted to larger angular scales. Conversely, in other regions of the sky, the CMB is demagnified, and so the local power spectrum is shifted to smaller angular scales. And so what this quadratic estimator is doing effectively is it's kind of stitching together measurements of the power spectrum in different small regions and using those to construct a field. So by looking at how lensing modulates the CMB statistics, we can go from a map of the CMB temperature to a map of the lensing deflection field. So we have this lensing map, which is the fundamental object. But as you know, in cosmology, we want to measure a power spectrum in order to do quantitative cosmology. So we take this lensing map and we measure its power spectrum. And that gives us the lensing power spectrum, which tells you how much lensing you have as a function of the angular scale. Now, in practice, that's actually a lot harder than you would naively think, because the naive thing to do is just take my quadratic estimator, which depends on 2 powers of the temperature, and square it to measure the power spectrum. The problem with that is that even if you have no lensing, the square of a quadratic estimator in T gives me 4 powers of the temperature map. And so even if I have no lensing and the CMB is perfectly Gaussian, this has a non-zero expectation value. And so to correct for that, what I need to do is I need to subtract off this bias, this sort of bias that's there even in the absence of lensing, and it's given just by the Gaussian, Wick's theorem contractions of this 4-point function. All right, and then I get a good estimate of the true lensing field. You'll recognize this probably as basically measuring a trispectrum, right? So one way of looking at semilensing is it breaks statistical isotropy. If I hold the lenses fixed. Another way, if I'm averaging over the lenses, is it induces a large or a substantial non-Gaussian trispectrum. So what I'm doing here is I'm measuring the 4-point correlation function and subtracting off the disconnected part to get the connected part. Okay, so that's how, and that's really a difficult step, but that's how we go out and we measure our lensing power spectrum. Now, why is this interesting? Well, as you know, lensing probes the mass density projected from all the way out to very high redshifts. So the overdensity projected with some kernel peaking around redshift 2, projected all the way to the last scattering surface. And therefore, the lensing power spectrum is just a projected version of the matter power spectrum. And so it's sensitive to several interesting cosmological parameters. It's sensitive to how much matter there is, so omega matter. And it's also sensitive to how clumpy the distribution of mass is, right? So therefore, which is parameterized by sigma 8. And so therefore, it is sensitive to some combination of sigma 8 and omega matter. And the combination of sigma 8 omega matter to the 0.25. So very similar to weak lensing, a little bit different because it comes from different redshifts. And so one motivation for making these precise measurements of the semilensing power spectrum is that we can test the S8 tension. So weak lensing is very powerful, but it's also very difficult. There's lots of challenges with photometric errors and shear calibration, et cetera. And it's intriguing that, if I look at a measurement of S8, sigma 8 omega matter to the 0.5, the Planck CMB value is up here. And, here's a compilation of the low redshift values, right? And, these are generally only 3 or less sigma discrepant, but it is interesting that there's at least some sort of weak hint that maybe the amplitude at low redshift is a bit lower. So it would be interesting to check that with a probe with very different systematics that is arguably quite clean. And in addition, we're getting even if that's just a fluctuation, we're definitely going to get a constraint on the neutrino mass that'll be quite powerful and quite robust. We've made a lot of progress in the last decade. So when we started working on this in 2011, these were some really terrible first detections at 4 sigma. But now with Planck, this has become precision cosmology. But what's cool is that ground-based CMB will do a lot better, and that's what I'll talk about right now. My students and I are currently working a lot on analyzing the latest data from the Atacama Cosmology Telescope, which is an arc-minute resolution CMB telescope high up in the Atacama Desert. And because it has high resolution, it can make really, really nice maps of the CMB that have really high resolution. So here's a map of the CMB. This is from the new ACT data. So this is not just a really high resolution map, as you can see from these individual bright point sources, which are a much higher resolution than Planck gets, but it's also now not just a small sky area. We've now observed something like half of the sky, which I think is really cool. So here you can see the galaxy. So this is around 17,000 square degrees. And what we've been doing now is analyzing this fantastic data set for lensing. From this really, really nice CMB temperature and polarization map, we've extracted a lensing map that is real signal dominated, like really signal dominated over a pretty wide range of scales. So what you're seeing here, these are real lensing structures. This isn't noise. This is a real lens that is, so there's a real clump of dark matter somewhere in that direction. And what's cool is that these are, getting to be really big maps. So, here you can see a, nearly half sky signal dominated mass map. So we've mapped the dark matter on half the sky. It's pretty fun. Yeah. Sorry, I'll just spend the rest of my time just scrolling around and looking at this map. What's neat is actually, it's because it's signal dominated, you can sort of do cross correlations by eye. So for example, I can take a high redshift large scale structure tracer that has very similar redshift to CMB lensing, like the cosmic infrared background, so emission from dusty galaxies, and I can compare the two maps with the same filtering. And what's cool is, you can see this cross correlation by eye, I think, at least. Hold on. So at least I seem to think that those look very similar. So, it's not surprising that luminous objects trace the dark matter, but it's nice to see that, illustrated on the sky like that, I think. Now back to sort of more quantitative cosmology, we're working very hard. In particular, my student, Frank Q, is working very hard, and I'm just telling him what to do and annoying him on getting this lensing power spectrum analyzed. And so given the noise, I can't show the final results yet, but given the noise that we have, we expect something like 60 to 70 sigma should be sort of achievable. So if we can actually get this to work, it will be really, 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 really cool, I think. And it'll be very powerful cosmological probe. So these are the forecast errors, but given the actual noise that we have in our measurement. Now, the problem though is, and I mean, I kind of thought initially that we would just be able to use the sort of standard Planck-like analysis pipeline on our ground-based data, but it turns out there's been several problems that have kind of arisen specifically from the analysis of ground-based data, which I think is kind of interesting. So Frank has been spending a ton of time solving these issues. And so one of them was that in some sense, the most basic null test you could think of was just failing. So this really basic null test that you can see here, so here are sort of the null test points. This is the expected signal, and these are null test points, and these should be 0, okay? And so what is this null test? Basically, it's running the pipeline on noise from the data. So what we did is what you do to get the noise, you take the first half of observations minus the second half of observations, schematically difference them, and then you get a noise map from data. And then you run that through your pipeline. In other words, you calculate the 4-point function of this map, and you subtract off the Gaussian part. And there's a very clever algorithm that Toshiya Namikawa and others and also the Planck team came up with that means that you can do this in a way that doesn't need your simulations to be that good. They just need to be reasonable, and then you can get your simulations can be your simulation power spectrum can be fairly wrong and it corrects for it. But so we have this very fancy pipeline that's sort of self-correcting for errors in the noise power in the simulations. And despite this fancy pipeline, when we just run on noise, we get a failure of the null test. Even though this algorithm was supposed to be robust to having, somewhat wrong simulations of your noise, we began to suspect that somehow our simulations were dramatically wrong, right? And so we switched then to a new estimation method that basically relies only on cross correlations. So effectively, you split your data into many independent splits, and you make sure to only use different splits in your 4-point correlation function. Like only use the first, divide it in n parts, and always make sure to use different parts in calculating this 4-point function. Now, this actually turns out to be harder than you would think, because the combinatorics, when you have a large number of splits, it gets huge, and you have to do this quickly. And so, you have to think a lot about how to do this. But what's cool is that then doing sort of just cross correlations fixes all our null test failures, right? I think the lesson here for me is that, and I think that maybe what's going on is that the atmospheric noise that we see from the ground has some kind of complicated properties. I think it might actually have a non-negligible trispectrum. And I think what we're seeing here is that our method assumes that the noise is Gaussian, right? But the actual noise that we are, I think, getting from the atmosphere has some sort of non-Gaussian trispectrum. And I think that's what was biasing us. And that was fixed then by going to these sort of cross spectra, because that gets nulled. We can do a forecast based on, or sorry, we can run chains based on our expected error bars. And this is kind of the constraint that we expect to get. So it's, I think 1.5 times better than kids. And if I put that point that we expect to get on the plot with all of these current measurements of S8, it is actually very interesting. It is quite a powerful point, and it hopefully will give us some insights into what the correct value of S8 is and whether there's something interesting going on or not. And then, of course, further in the future, we will have Simon's observatory, which will improve these constraints by at least another factor of 2. So I think sigma 8 and neutrino mass measurements from these lensing power spectra will be very interesting, even in a year or so time scale, I hope. All that's left is to just wrap up, and I'll leave you with my summary. And if you have any other questions, feel free to ask.